Okay, so here we talk about how to calculate the potential due to a charged particle, so which is the most simple case, the easiest case. So yeah, so actually we follows the definition. Okay, so the electric potential difference between 2 point I and F is Vf minus Vi equals to this negative of the line integral. And here, okay, so here we try to consider Vf, okay, the final point is at infinite far away, okay, it's at infinite far away. And then Vi, okay, so this is Vi, sorry, Vi at this point, okay, at this point. And then the point charge is here, okay, so we would like to see the potential generated by that one, okay. So and then Vf is actually at infinitely far away. Okay, so we try to move it from that point to there. Okay, so here we try to consider the axis. Okay, this is the R axis. This is the R axis. This is the 0 point. This is infinity. Okay, and then this is the R. Okay, so actually, or maybe first reconsider. Okay, so I think it start from this point instead. Okay, start from this point instead. Okay, start from, okay, so I mean this one should be the initial point. Okay, so this is just a point in between. Okay, this is just a point in between. Okay, so start from this capital R. Okay, so actually we try to integrate E dr. Okay, so I think the ds is actually, yeah, ds and E are actually points to the same direction. Yeah, because we already know that the E field, okay, from this positive charge is actually pointing upward along this axis. Okay, so E and ds points to the same direction, so it becomes E times dr. Okay, we'll say this is the R axis. So the integration is evaluated from capital R to infinity. Okay, so this is yeah, this makes sense, hopefully. Yeah, so here what we have is this one. Okay, E equals K times Q over R squared. This is what we have at the very beginning at in chapter 22. Okay, E equals this expression. E have this expression. So so Vf is at infinity. So Vf is 0. Vi is what we want to find is denoted as V. Okay, so plugging this 0 and V to here and here, so it becomes 0 minus V, and we plug in E to here. Okay, and then Q and this 1 over 4 pi epsilon naught is independent to dr, or is independent to R, so we can put this and this in the front. Okay, only R square is a function of R, so we have a dr over R square integration from capital R to infinity. Okay, so this is a polynomial, okay, with a negative exponent. So this is R to the negative 2 power, so plus 1 is R to the negative 1 power, so we have a 1 over R here, and then with a negative sign. Okay, we need to divide it by negative 1. Okay, so this negative 1 and this negative sign turns out to be a positive 1. Okay, so we have a positive Q over 4 pi epsilon naught, and then 1 over R evaluated from capital R to infinity. So by substituting, so Q, so it will become Q over 4 pi epsilon naught 1 over infinity minus 1 over R. Okay, so this one is actually 0, so negative, so equals negative 1 over 4 pi epsilon naught times Q over capital R. So here we have a negative sign, we also have a negative sign here, so multiplying negative 1 on both sides. Okay, so it becomes V equals 1 over 4 pi epsilon naught Q over R. Okay, and then we replace R by capital R by small r. Okay, so we get this expression. Okay, we get this expression. Okay, V equals K times Q over R, which is the electric potential generated by a point charge. Okay, so here, if we have multiple charges, the potential due to a collection of charged particles is V equals the summation of Vk, which is K times summation of Qk over Rk. Okay, because 1 over 4 pi epsilon naught is a constant, so we put this term in the front. Okay, only Qk and Rk are related to this K. Okay, so it somehow look like what we do for the Coulomb's force and E field, but the difference is that Coulomb's force, E field are vector field. Okay, here the potential is a scalar field. Okay, so which means that we add scalar together, which is easier, because if we need to add many E field together, which means we need to decompose it all the E field along, for example, x-axis, y-axis. Okay, we have x-axis component for all the E1, E2, E3, or the y-axis component for them, and then we add all the x-axis component together, all the y-axis component together, to finally come up with the sum of the E field. Okay, so thus the potential is the algebraic sum 代数和 of the individual potential with no consideration of directions. Okay, so here's a highlight. The positive charge particle produce a positive charge particle produce a positive electric field, and a negatively charged particle produce a negative electric potential. So it's very straightforward. So here is a quick track point. This is easy, but you need to get used to it. Okay, so usually when I ask it during the class, usually it will be wrong. you have a wrong answer. Okay, so anyway, let's try this again. So here we have so here three figures. So figure here show three arrangement of two protons. Okay, two protons means they both have a charge of positive E. Okay, positive E. Okay, rank the arrangement according to the net electric potential produced at point P by protons greatest first. Okay, 就是要求这个 P 点的 potential 从大到小。Okay, so for the figure A, okay, P is on the left, two protons. Okay, one is here, one is there. Okay, so we have small d, we have another capital D. Okay, so we only know that capital D is larger than small d. Okay, we don't know the ratio between them, but it doesn't really matter. Okay, so we only know that P is here, small d, okay, d, small d, and then capital D. And then the second one, P is here, okay, one is on the left side, capital D, one is at the bottom, small d. Okay, the third one, P is in the middle, one is on the left, small d here, and then one is on the right, capital D. Okay, so which is the largest one? Which is the greatest one? The potential at point P. Who think A is the greatest one? No. B. Okay. C. No. Okay. So, what is the answer? Okay. So maybe you are smarter. So yeah. So actually, the question is. Yeah, so maybe you say the question is a little bit tricky, okay? As who is the greatest, okay? But actually, the potential are the same potential. Same potential for ABC. For A, B, and C, yeah, because it's only a scalar sum, okay? So for all the three cases, V will be K. Okay, K is actually 1/4 pi epsilon naught times E, and then 1 over small d plus 1 over capital D. Okay, so this is for all the three cases. Okay, so the two terms are just add together as a scalar sum, so it doesn't relate it to the direction, okay? But of course, only for that point P, okay? For other point, okay, so they are not different. Okay, so yeah, so let's move on. Okay, so here we have another sample problem. Okay, so here we have 1, 2, 3, 4. Okay, so Q1, Q2, Q3, Q4. So what is the electric potential at point P located at the center of the square? Okay, so this is the center of the square of the point charges. The distance D is 1.3 meter. Okay, so 1.3, 1.3, 1.3, 1.3. And the charges are Q1, Q2, Q3, Q4. Okay, so if you are supposed to find the E field at point P, that will be quite tedious. Okay, so you need to find several E field and then decompose it. Okay, but for actually for this one is a square. Yeah, you don't need to decompose it or not because so the opposite charges, okay, so actually point to opposite direction, so they can easily cancel each other, and then finally you turns out to have a two orthogonal component. Okay, so you can, so for this case fine, but if you are supposed to find the electric potential here, so it will be even more simple. Okay, so actually what we need to know is the R first. Okay, so as much as it is the center, okay, so all the R are the same. Okay, R will be D over square root of 2, okay, due to the Pythagorean theorem. Okay, because this is a square, it's a center point, okay, so 45 degree, okay, and then this is all the way right angle triangle, okay. So this is D and then square root of D for here, D over square root of 2. Okay, so the V will be summation of Vk, k from 1 to 4. Okay, we all together have 4 charges. So this is nothing but k times Q1 over R plus Q2 over R plus Q3 over R plus Q4 over R. So it is nothing but K over R and then Q1 plus Q2 plus Q3 plus Q4. So this is 8.99 times 10 to the 9th power, and then R, what is R? D is 1.3. 1.3. Okay, so this is nothing but 1.3 over square root of 2. Okay, and then we have Q1, Q2, Q3, Q4, 12 plus negative 24 plus 31 plus 17. Okay, and then times nano. Okay, I'm not sure whether you have memorized the periodic, the scientific prefix. Okay, I have added on the slides in chapter 22. Okay, so if you haven't memorized the scientific prefix yet, okay, so try to go back to the lecture note for the chapter 22. Okay, so yeah, so actually the nano is 10 to the negative 9th power. Okay, so this is for nano. So as I have mentioned it before, during the quiz or exam, you need to memorize the scientific prefix by yourself. You cannot, even though you ask, I will not answer. Okay, you can ask other meaning of, so ask the meaning for other words, but you cannot ask, what is nano, what is pico, something like that. So actually this is nothing but 350 volt. Yeah. Okay, so for this question, it's just ask you, it just asks you the potential at point P. Yeah, but actually the figure here just tells you that, okay, this is the equipotential surface. Although it's only on a plane, so it is like an equipotential line. Okay. So yeah, but don't try to ask why the shape will be like that. Okay, so actually probably you need to use a computer program to find, okay, so all the point, okay, so try to plot many scatter point. Okay, you try to calculate all the V at different point, and then you try to find, okay, all the point are 350. Okay, but at very least you will know that this line should encircle Q1, Q3 and Q4, because Q1, Q3 and Q4 are positive. This is plus 12 nano C. Okay, this is negative 24 nano C. This is plus 31 nano C. This is plus 17 nano C. Okay, Q1, Q3, Q4 are positive. Okay, Q2 are negative. So the equipotential surface should encircle them. Or either somehow lie between. Okay, so either encircle all of them or enclose nothing. Okay, it can be somewhere between. Yeah, because at this point should be infinitely large. At this point should be infinitely large. Should be, yeah. Yeah, or maybe something like that. Okay, there could be something like that. Okay, and then finally, okay, this line would encircle all this one. Okay, but it can never encircle positive charge and negative charge. Okay, yeah, so here we have another sample problem. So here it says we have 12 electrons, okay, of charge negative E are equally spaced and fixed around a circle of radius capital R. Okay, so here, like a clock, we have 12 electrons, and then the radius is capital R relative to V equals infinity at infinity. Okay, so it's usually always an assumption for the equipotential problems. Okay, so V equals 0 at infinity. What are the electric potential and the electric field at center C of the circle due to these electrons? Okay, so V is nothing but K times negative 12E over capital R. Okay, so nothing special. This is K, and then adding all the charge together. Okay, all are electrons, negative E, so totally 12. So negative 12E over capital R. So this is V, okay, and then for E, okay, actually they will all cancel. So for example, this one and this one, okay, this is negative E, this is also negative E. So picking these two pair, okay, are on opposite side. So for the top one, okay, it will generate E field pointing upward. For the bottom one, it will also generate E field pointing downward. Okay, so between these 12 electrons, okay, you can pair it. You can pair up. You can also together have 6 pairs of electrons. So each pairs cancel. Okay, generate E field, but will be cancel each other. So total E field will be 0. Okay, will be 0. Okay, at point C. Yeah. So this is the other one. Okay, this is the potential. Okay, for question B, it asks if the electrons are moved along the circle until they are non-uniformly spaced over a 120 degree arc. Okay, like this. What then is the potential at C, and how does the electric field C change, if at all? Okay. So here V doesn't change at all. It only related to the charge amount and the distance. Okay, actually all the charge still have the same distance to point C. Okay, so it is still negative 12E over capital R times K. Okay, will be the V at point C for the question B. Okay, so actually the same as A. Okay, the same as A. Okay, but here E won't be different. Won't be 0. Okay, E won't be 0 here. Okay, yeah, because they cannot cancel. Okay, so that's why we need to define. Okay, sometimes they are the same, sometimes they are different. If they are all the times the same, then you don't need both of them. Okay, as long as they, sometimes are different. Okay, so both of them are useful. Okay, so so this is easy. So let's move to the other parts. So the potential due to a electric dipole. Okay, so if you still remember in chapter 22, we have learned something called the E field due to electric dipole. But at that time, we can only know the expression of the E field along the z-axis at that time for the E field. Okay, if it is out of the z-axis, the expression is not simple enough to be used. Okay, so we only have an elegant expression as long as the point on the z-axis. Here, for the electric potential, because it is easier to calculate, okay, we can actually consider any point in the space. Okay, we can consider any point in the space. So here, the net potential P at P is given by V equals V plus V minus. Okay, we have for an electric dipole, we have two charges with the same magnitude but opposite sign are placing close together with a distance d, and then one is positive q, one is negative q. Okay, face together. So so when we consider the V at point P, okay, so actually we have two charges. Okay, so we add the potential generated by the positive charge and the potential generated by the negative charge. Okay, so that will be K. Okay, this is K, Q, and then negative Q. Okay, and then one is R plus, one is R minus. So from the figure, this is R plus, this is the positive charge, this is R plus, this is the negative charge, this is R minus. Okay. Now we try to have some approximation. Okay, we actually assume that this point P is far away. Okay, how far is that? Yeah, so this R is much larger than D. Okay, so here we assume that this R is much larger than D, much larger than this, the dimension of the dipole. Okay, so here we still have the far field condition. Okay, if it is very close, the expression is still very, the electric potential is still very messy. Yeah, but here we still assume that P is very, very far away. So in that case, suppose this P is far away enough, we can assume that this and this, okay, these two, okay, P is very, very far away. So, okay, so P is also here, okay? Yeah, but P is very, very far away. So we consider this line and this line are parallel to each other. So maybe hard to imagine, but yeah, you just try to imagine that, okay, so this P is very, very far away, then these two lines become more and more parallel as long as P is farther and farther. So as long as P is infinitely far away, and then we can assume that R plus R minus. Okay, so these two lines are parallel to each other. Just like when you assume the sun, okay, so the sun shines to the earth, okay, so you consider all the ray from the sun parallel lines. Okay, just like that. Okay, so here, okay, so here R plus R minus, we do not consider a known value or a good variable for the final expression. We just try to use the R. Okay, so the R. The R means the P, the point P to the middle point of the electric dipole. Okay, so it's the small r. We try to use this r in the final expression. Okay, so of course, this r will be lie somewhere between them. Okay, but actually, what we would like to find is r plus r minus. Okay, so before going to that figure, we try to first we try to factor out the q, okay, the common factor q, okay, and then we try to subtract them. Okay, this R is much larger than D. Okay, here. So this is like this is actually like a 1/4 pi epsilon naught Q, and then 1/r plus minus 1 over r minus, something like that. Okay, so if we subtract them, we will have a common denominator, r plus r minus, and then we will have r minus r plus, okay, in the numerator. Okay, so here what we want to know is r minus r plus, okay. So suppose, okay, suppose P is here, okay? And then, so this is R plus, this is R minus, okay? So what it means is that, okay, so this will be a rectangle, okay? What I mean is this will be a rectangle. This will be a rectangle. Okay, so which means that this part will be R minus R plus. Okay, this is R minus, this is R plus. Okay, so this part will be R minus R plus. Okay, and then what it is that this is D, and then we assume this is theta. So this part will be D times cosine of theta. D times cosine of theta. Okay, so this side over this side will be cosine of theta. Okay, so here we have R minus R plus is approximately D cosine of theta. Yeah, because we assume that P is infinitely far away, so there's the difference between R minus and R plus will be D times cosine of theta. And then R plus R minus will be approximately R itself. Okay, yeah, as much as P is infinitely far away. Okay, so actually we try to plug this one back to here. Okay, back to here. So we have V equals Q over 4 pi epsilon naught, and then D cosine of theta go to here, and then R squared go to here. Okay, so if you still remember, we actually have defined the electric dipole moment, which is P equals QD. So here we can just write it as this is K, P cosine of theta, and then R squared. R squared. So this is actually the potential generated by a dipole, as long as R is much larger than the D. Okay, R is much larger than D. Okay, with the far field assumption. Okay, so actually this V is actually useful for antenna design. Okay, 天线的设计. Okay. So actually it tells you that the potential is related to the angle. So of course this is not with a dipole as the antenna. Yeah, I don't think you have seen the very old mobile phone like 20 or 30 years ago. Okay, actually at that time I'm still very small, but at that time. Yeah, at that time the mobile phone can be like this one, and then with another antenna. Okay, very long like that. Okay, so that one is so-called the dipole. Okay, the dipole, and then it actually tells you that, okay, so the potential generated by the antenna is related to the angle. So maybe, okay, it has cosine theta. Theta means the angle between the dipole. Okay, so which means that if the dipole is something like this, okay, so this direction have the strongest potential, this time, but this direction will have a zero. Will have a zero potential, okay, if it is perpendicular to it, okay. If theta is 90 degree, cosine of 90 degree is 0. Cosine of 0 degree is 1, okay? So if it is along the dipole, okay, so the potential will be maximized. Of course, if it is opposite side, it is negative, but the magnitude is still maximized, okay? But if it is perpendicular to it, then the potential generated by this dipole is minimized. Okay, but actually so for the antenna design for your smartphone, it has some design. Okay, so that it try to generate the EM wave, on this side, but try to maximize it this side, so that when you try to, let's say you just talk with your phone, okay, so most of the EM wave go to that side, okay, rather than go to your brain to hurt your brain. And actually, if you want to have a higher transmission rate, just say, that is the router. There is a router near the ceiling. Okay, so if you use your phone direct to it, okay, so that you will have a faster transmission rate. If it is like this, okay, you need to rely on the refraction. Okay, you need to rely on the refraction. Still, if you can see it in the line of sight, then it will be fine. But if you can direct to it, it will have a faster transmission rate. Yeah. Okay. So next, potential due to a continuous charge distribution. Okay. So just so what we done in chapter 22. First single charge, next multiple charge, and then next continuous distribution. Then we need to cut it into many small pieces, and then we try to find the small v, and then add them together as an integral. Okay. So this is what we done here. Okay, so for continuous distribution charge, the potential is found by dividing the distribution into charge element dq that can be treated as particles, just as what we did before, and then we try to add the potential together. Okay, but previously adding the dE together, dE is a vector. Okay, is a vector. So we need to decompose it in x-axis, y-axis, or even z-axis component, and then we try to cancel part of the components and then add the remainings. But here, dv is a scalar. Dv is a scalar, so we try to add all the scalars together, which is easier. We don't need to decompose it. So finally, it turns out to be dv. Okay, previously we have a v equals 1 over 4 pi epsilon naught times q over r. So we can actually rewrite it as dv equals 1 over 4 pi epsilon naught is a constant. So we have a dq over r, okay, something like that. We just change v into dv, q into dq, okay. So we try to put this one here, okay. So 1 over 4 pi epsilon naught go to the front, dq over r. Of course, for different dq, r might be different. So we tends to put the r inside the integral side. Okay, so here we have a line of charge. Okay, so here figure A have a thin conducting rod, length capital L, as shown in figure B. Figure B is here. The element of the rod has a differential charge. dq equals lambda dx. Okay, so just as what we have mentioned before, this lambda is the linear charge density. Density. Okay, linear charge density. Okay, if you forgot linear charge density is, just go back to chapter 22. Okay, you need to do some revision because we will have a quiz next Friday. Yeah, so dq equals lambda dx. So what we want to find is the potential at point P generated by this rod. Okay, generated by this rod. Okay, so here we superimpose the x-axis here. Okay, this is the x-axis. This is 0. This is capital L. Okay, so in that case, this is 0. This is L. This is this is x-axis. Okay, so here we have dx. We have dx. Okay, and this is, we have a distance d here. Okay, so for this part d, okay, we will have a distance from this dx to point P with a distance r. Okay, so we have a dv equals 1 over 4 pi epsilon naught dq over r. Okay, this is what we have originally for a charged particle. Okay, so here we try to plug in this one to here. So we have a lambda dx, and then for r, this one is a right angle triangle. Right angle triangle. This is x. This is x. Okay, so this is a right angle triangle. So we have, according to Pythagorean theorem, r equals square root of d squared plus x squared. Okay, so here we have r equals square root of x squared plus d squared. Okay, so v is integration of dv. Okay, and then we plug in this one to here. So lambda goes to here. 1 over 4 pi epsilon naught go to here. So the remaining stuff are these parts go to here. Okay, we have dx, and then x squared plus d squared to the negative 1/2 power. Okay, this square root is in the denominator. Okay, so we make it like this. Okay, so if you just refer to the calculus table, okay, the integration table, this definite integral is this. Okay, has this expression, lateral log of this stuff. Okay, but if we would like to do it by yourself, okay, I just show it how we can work it out quickly. Okay, for this one we have x squared. Okay, x is the integration variable. This is a constant, so we always make the assumption of the change of variable as x equals the tangent of theta. Okay, so we take the derivative from both sides. Dx equals d. Okay, so don't mix this d with the differential. Okay, this d is this. Okay, so try to be careful. This d is the length. Okay, so don't try to mess it up with this one. Okay, so here we still have this d in the front. Okay, but take the derivative of the tangent theta. Tangent theta is a variable, so we have a secant theta square d theta like this. Okay, so here we have a x squared plus d squared will be d squared. Okay, so this is also this d squared. Okay, 1 plus tangent theta square, which is still d square secant theta square. Okay, so this is trigonometry. Okay, Yeah, hopefully you still remember the trigonometry formulas. Yeah, so this is the preparation. We need to calculate this integral. Okay. So here we try to change the variable. Let's say this is I. So I equals integration of this one. Okay, we have this one as this one. Okay, that will be d over 1 over d secant theta. Okay, take the square root and then put it in the denominator. And then for the dx is this one. Okay, we have a d secant square theta d theta. Okay, so we actually can cancel many things. This d with this d, this square with this one. Okay, we only left with the secant theta d theta. But what is the lower and upper bound? Okay, lower and upper bound. Okay, we actually need to draw a right angle triangle. Theta L. This is L. Or maybe like this. Okay, this is L. This is L. This is D. This is D. This is theta L. This is theta L. Okay, yeah, because actually if you go to the last point, okay, the last point actually is the L. Okay, we consider this is the theta L. And then for the very first point, this point, the angle will be 0. Okay, so it will be from 0 to theta L. Okay, so next step will be, we only left with integration of secant theta d theta from 0 to theta L. Okay, so this is the trick you need to remember if you need to integrate the secant theta, is to multiply secant theta plus tangent theta. Okay, this is the trick you need to remember. Secant theta plus tangent theta d theta from 0 to theta L. Okay, so here we have this one. To reverse the chain rule, it turns out to be d tangent of theta plus secant of theta, okay, over secant of theta plus tangent of theta. Okay, because you take the derivative of tangent theta will be secant square. You take the derivative of secant square will be secant theta plus multiplied by tangent theta. Okay, so this is the reverse of the chain rule. Okay, so theta to theta L. Okay, so this is good because this one and this one are the same. Okay, so it turns out to be integration, lateral log of secant theta plus tangent theta. Okay, and then evaluate from 0 to theta L. Okay, so lateral log of secant theta L. Okay, so according to this right angle triangle, this is d squared plus L squared. Okay, so secant theta according to this one will be square root of d squared plus L squared over d. Okay, tangent theta will be L over d. Okay, tangent theta L. Okay, also according to this one. So which means that this is nothing but d and then L plus square root of d squared plus L squared minus lateral log of secant theta 0 plus tangent 0. Okay, tangent 0 is 0. Secant 0 is 1. secant 0 is 1, okay? 1 over cosine 0 is also 1, okay? Natural log of 1 is 0, okay? So this whole term turns to a 0. Okay, so finally, we have natural log of L plus 0 of L squared plus D squared over D. Okay, so just swap it around. Okay, so this is how we can tackle this integration. Okay, so that's why it is like that. Okay, so maybe we